All right, let's jump right into this explainer. Welcome in, everyone. So today, our goal is kind of simple, but also pretty ambitious. We are going to strip away all that intimidating command line jargon and give you a really clear visual blueprint of how Git actually works right under the hood. You know, whether you're a solo developer hacking away on a weekend project, or you're working in a massive Fortune 500 enterprise, Git is absolutely the non-negotiable bedrock of your daily work. But let's be honest. So often, we all just memorize a few terminal commands without really understanding the system we're using. Well, today, we're going to change that. We're going to look at the true architecture of version control, and we're going to make the complex beautifully simple.
To really understand why we even need this architecture in the first place, I want you to picture this. Imagine you're writing a 400-page novel. After months and months of painstaking work, you decide to totally rewrite chapter 12. But when you finish, you realize the new version is actually way worse than the old one. If you only kept one single copy of that document, you have absolutely no way to go back. Your original brilliant work is just gone, forever. Now, take that exact problem and multiply it by 500 engineers, all working on the exact same code base simultaneously, tweaking thousands of files and building dozens of different features. Without a bulletproof system to track all of those changes, software projects of even modest complexity would literally descend into absolute chaos.
So here is our blueprint for the explainer today. We'll start with the version control problem, then look at the 10-day Git revolution. After that, we'll dive under Git's hood, explore modern collaboration and branching strategies, and wrap up with the AI and Git 3.0 frontier.
Kicking things off with part 1, the version control problem. From chaos to collaboration.
Let's briefly trace the history that paved the way for modern software engineering, because the journey to reliable version control definitely did not happen overnight. Back in 1972, we had SCCS, which could only track changes locally on a single machine, and literally just one file at a time. Then in 1986, CVS brought a huge breakthrough: concurrent work on a shared server. Though, to be fair, branching and merging were still notoriously unreliable. Fast forward to the year 2000, and Subversion, or SVN, became enormously popular. It fixed a ton of CVS's flaws by introducing atomic commits, meaning updates were all or nothing. But SVN had a massive, fatal weakness. It was centralized. You needed network access to do almost anything, creating a huge single point of failure. Meanwhile, the open-source Linux kernel community was using this proprietary distributed system called BitKeeper. But in 2005, boom, a massive crisis hit when BitKeeper's free license was suddenly revoked. And this crisis essentially forced the Linux community to find a new solution, and they had to do it fast.
Which brings us nicely to part 2, the 10-day Git revolution, building a better system.
So in response to that whole BitKeeper crisis, Linux creator Linus Torvalds decided to just step up and write his own solution. He built the first working version of Git in a legendary 10-day sprint. 10 days! His design goals were explicitly tailored for the Linux kernel itself. It had to be blazingly fast, it had to support nonlinear development with thousands of parallel branches, and it absolutely had to be fully distributed so no one was ever dependent on a central server again. And you know what's kind of hilarious? He named the software Git, which is actually British slang for a stupid, unpleasant person. Torvalds humorously claimed that he just names all his projects after himself. But jokes completely aside, the software he created in that sprint fundamentally changed how the entire world writes code. Now, the really crucial point here is understanding exactly why Git won the version control war. It wasn't just, slightly better. Its underlying philosophy was a total paradigm shift. Legacy systems like SVN stored file changes as a series of diffs or deltas. Basically, if you wanted to view an old version of your code, the system had to rebuild it on the fly by calculating all those historical differences. This made switching branches incredibly slow and computationally expensive. Git, on the other hand, takes a completely different approach. It stores complete snapshots of your entire project at every single commit. If a file hasn't changed from one commit to the next, Git doesn't duplicate it. Instead, it simply creates a tiny, lightweight pointer to the already stored version. And because Git always has the full state of the project immediately available, viewing your history or switching branches is practically instantaneous. It's a real game changer.
All right, let's roll up our sleeves. Part 3, under Git's hood, the core engine.
Let's dive into the actual plumbing of Git and translate what looks like a really daunting architecture into a beautifully simple narrative. At its very heart, Git is essentially a content-addressable file system. Everything is stored as an object. And the most foundational object of all is the blob, which stands for binary large object. A blob is literally just Git's way of storing the raw content of a file. And here is the mind-blowing part. A blob does not store the file's name. It doesn't store its permissions or its file path. It only stores the text or binary data inside the file. Git identifies this blob by generating a unique cryptographic SHA hash with the content itself. So what does this mean for you? Well, if you have 100 identical configuration files scattered all over your project, Git automatically deduplicates them. It saves that chunk of content exactly once and just creates 100 lightweight references to it.
And this brings us to how all those objects are actually tied together. The Directed Acyclic Graph, or DAG. This is Git's permanent immutable backbone. Every single commit you make is a node in this graph, and every commit points backward in time to its parent commit, creating a one-way edge. Now, because commits always point backward, and you obviously can't commit something that depends on the future, the graph can never loop back on itself, hence the term acyclic. The strict mathematical structure is exactly what prevents corrupted histories, and I love this analogy. In this immutable DAG, a branch is not a copy of a folder like it was in older systems. A branch is literally just a tiny text file with a hash in it. It's basically a post-it note slapped onto a node in the graph. You can peel that post-it note off and stick it on another node instantly, which is exactly why branching in Git is practically free.
So let's see how this all builds into your daily workflow using the 3-area model. This is exactly how a commit is born. First up, you have the working directory. This is just what you see on your computer screen. It's where you're actively typing and editing files. Second is the staging area, sometimes called the index. And man, this trips up so many beginners. The staging area is basically a draft buffer. When you run git add, you aren't actually saving anything to history yet. Actually, scratch that. You're just promoting those specific changes into this draft zone. It's awesome because it lets you pick specific files or even specific lines of code to bundle together logically. Finally, step 3 is the repository itself, that hidden .git directory. When you run git commit, Git takes everything you prepared in the staging area, packages it into one of those snapshots we talked about, and permanently writes it to the immutable object database.
Moving right along to part 4, collaboration and branching strategies, working together. Now that we know how the engine works, let's explore how modern engineering teams actually use it to collaborate, because choosing how your team branches and merges is absolutely crucial. For years, a strategy called Git flow was highly popular. It uses multiple long-lived branches like develop and release. It's super structured, making it really best for software that requires long-term support versions like a traditional desktop app. But honestly, all those long-lived branches often lead to massive, painful merge conflicts. Nobody likes those. Today, the industry has aggressively shifted toward trunk-based development. This model relies on a single shared trunk, usually just your main branch, and developers use very short-lived feature branches, merging updates back in constantly. Extensive research from the DevOps Research and Assessment Team, known as DORA, consistently links trunk-based development to elite organizational performance. It's faster, you get way fewer merge conflicts, and it is absolutely perfect for modern continuous integration pipelines.
Of course, regardless of your branching strategy, you are eventually going to have to integrate your changes. Merging joins histories together, but rebasing rewrites them to create a super clean, linear timeline. Rebasing is incredibly powerful, but it comes with a massive warning label. You need to treat this quote as an absolute law of physics. The golden rule of rebasing is never rebase commits that exist outside your local repository and that someone else may have based work on. Why? Because rebasing literally changes the cryptographic hashes of the commits. Rewriting public history creates a chaotic, diverged nightmare for everyone else on your team. So please, for the love of your coworkers, keep your rebases local.
And, breaking that golden rule is really just one way things can go wrong. Let's quickly run through some of the most common pitfalls developers make. Number 1, and this is a biggie, committing secrets like API keys or passwords. Because Git's history is totally immutable, if you accidentally commit a secret, simply deleting the text in your next commit doesn't work. It's still right there in the history. You have to rotate that key immediately. Other major pitfalls include force pushing to shared branches, which literally overwrites your colleagues' hard work, or making these enormous end-of-week commits that are just impossible for anyone to actually code review. Lots of developers also bypass the staging area entirely, losing all that precision, or they write terrible commit messages like fixed bug that tell future developers absolutely nothing. Oh, and finally, failing to set up your .gitignore file means you're definitely going to accidentally track a bunch of useless, heavy local build artifacts.
And finally, we arrive at part 5, the AI and Git 3.0 frontier, looking to 2026 and beyond.
Zooming out for a second,
Let's look at where the landscape surrounding version control is actually heading next. Because the way we interact with code is fundamentally shifting. Git is no longer just for human collaboration. It's quickly becoming the primary interface for autonomous AI coding agents. Think about it. AI assistants like GitHub Copilot don't just magically write code out of nowhere. They rely incredibly heavily on the structured history that Git provides. By analyzing the DAG, that directed acyclic graph we talked about, these AI agents can understand the evolution, the conventions, and the deep context of a codebase. This historical context is exactly what allows them to autonomously draft highly precise pull requests, refactor clunky legacy modules, and even attempt automated conflict resolution. Basically, Git's structured history is the textbook the AI reads to learn everything about your specific project.
But as our tools evolve, the underlying security of Git has to advance right along with them. I want you to really focus on this number for a second. 64. That is the character length of the new SHA-256 hashes. See, since its inception, Git has relied on SHA-1 hashes to identify all those objects. But SHA-1 has known cryptographic vulnerabilities now. Researchers have proven that hash collisions are a very real threat, so the upcoming transition to Git 3.0 is largely defined by this monumental migration away from SHA-1 over the far more secure 64-character SHA-256 algorithm. It is a massive undertaking for the entire ecosystem. Every script, every tool, and every hosting platform has to be updated to handle these longer, secure fingerprints. But it's absolutely crucial because it fundamentally hardens our software supply chain against really sophisticated attacks.
Wow, we have covered a lot of ground today. We've traveled all the way from the rudimentary single-file tracking tools of the 1970s right through Linus Torvalds' frantic 10-day sprint, deep down into the plumbing of blobs and graphs, and now we're standing right on the edge of an AI-driven future. Version control is clearly no longer just a simple developer utility, it is quite literally the infrastructure of modern digital creation. But it leaves us with this really fascinating, provocative thought to consider. As autonomous AI agents increasingly read the history, write the code, and mathematically resolve conflicts directly within the directed acyclic graph, how will our human relationship with Git evolve in the years to come? Are we eventually going to step back, acting merely as reviewers of histories written entirely by machines? It is such an incredible time to be building software. Thank you all so much for diving into this explainer with me, and hey, keep exploring.